Welcome to today's Postgres conference webinar, OtterTune, an automatic database configuration tuning service. We're joined by Andy Pavlo, co-founder of OtterTune, who will present an overview of OtterTune, discuss the challenges one must overcome to deploy an ML-based service for DBMS, and highlight the insights learned from real-world installations of OtterTune. My name is Lindsay Hooper. I'm one of the Postgres conference organizers, and I'll be your moderator for this webinar. A little about your speaker. So Andy is an associate professor of databaseology, which, by the way, is an awesome word, in the computer science department of Carnegie Mellon. He's also the co-founder of OtterTune, and he received his PhD in computer science from Brown. Welcome. So with that, I'm going to hand it off. Take it away, Andy.
All right, thanks, Lindsay. So databaseology is a made-up word, but the university thinks it's real, like neurology or psychology. So every time they have me go to like some kind of internal event, my name tag always says it and always makes me laugh. So okay, all right, guys. So we're here to talk about OtterTune. It's an automated database tuning service that we've been developing both at the university and then now spun out as a commercial startup. So for today's talk, I'm going to give some background. If the clicker works, got some background on what knob tuning looks like. Then I'll describe what OtterTune can actually do and how it works. And then I'll talk about two field studies we've done in the last two or 3 years of actually running OtterTune on real workloads at real customers running on real databases. Okay. All right. So knob tuning is sort of this important problem in database systems because it can really affect the performance of a system. So by database knob, I mean it's a runtime parameter that a database system exposes to you as a user that allows you to change the runtime behavior of the system. So think like buffer pool sizes, caching policies, log file sizes, and so forth. So every database system exposes these different knobs. There isn't a standard taxonomy across them, right? They all have their own thing. And so if you can tune these knobs correctly for your database system, you're essentially sort of customizing the data system for the application that's running on it, right? And the reason why these knobs exist is because as the database developer was building the system and they added a new feature, there's some decision they had to make about the functionality of the system, like how much memory should I allocate for this buffer? And rather than hard coding a value that might not, sort of might be, good enough for most people, but not everyone, they then expose it as a knob, and because they assume that a human's going to come along that's going to know how the application wants to run queries or execute transactions on the database system, and they can tune that knob specifically for themselves. But the challenge is that with over the many years that these systems have existed and all the new features that they keep adding, the number of knobs that these systems have or exposed to you is growing, and it's sort of surpassed the ability for humans to actually reason and manage them. Just not only within a single database, but now think about it, if you have a large number of databases, if you have a large fleet of Postgres databases, if you have to tune every single one individually, that can take a long time, and it's just not sort of feasible for a human to do this. So to give you an idea how bad this problem is, this is a survey that my PhD student did where she looked at the last 20-year release history of the two most popular open source databases, MySQL and Postgres. And then for every new release, she just looked in the documentation and counted the number of knobs that these systems had. So you can see at the beginning of the century, both Postgres and MySQL had less than 100 knobs, but then over 20 years, MySQL grew by 7x and Postgres grew by 5x. Now, admittedly, not all of the knobs here will affect performance, right? Some of these knobs are file paths, port numbers, host names, right? Things that you wouldn't want an automated system to tune because if you don't set those things correctly, the system's not going to run. But there's still dozens and dozens of knobs that will affect performance in these systems. And just, again, the complexity grows over time. So my OC is quite mirrored light. All right, we ignore that. Sorry. So how are people tuning databases today? So you basically have 4 approaches. The first is you can do it yourself. And what we often see at some organizations is that whatever person who set up Postgres or MySQL or the database at their last job, at their last company, is now, they throw, the problem at them to help set it up at the new job, at the new company, right? And this person is a programmer. They may not know the intricacies of database systems, and they're just going to sort of do, just try to do something really simple to get up and running. And so what they're often going to do is just Google, Postgres tuning or MySQL tuning, and there's going to be all these blog articles that describe, hey, here's the 5 knobs you should tune for your Postgres database or MySQL database. And that's about it. Even though there's dozens of knobs you could be tuning, these blog articles really only cover the most basic ones. Furthermore, in our own experiments and our own studies, we often find that some of what they recommend in these blog articles are actually incorrect for one particular use case or application. These might be like the lowest common denominator, good enough for most people, but for if you want to actually really fine tune the database system, oftentimes these recommendations are incorrect. All right, so say you don't want to do it yourself, although again, this is more common in the DevOps role. So say you have money and you can try to hire a DBA to come tune the database system for you. Well, one, the challenge is finding someone who's an expert and is available to tune these systems. But now the second challenge is going to be actually paying for them. So DBAs are not cheap, right? So this is some numbers from the Bureau of Labor Statistics from 2019. And then the average wage or average salary of a DBA was around $96,000 a year. Again, that's the average on the East Coast and the West Coast of the United States. Certainly, they're going to be way more. And when you think about this, though, also, the DBA is not just doing database tuning. They're doing a bunch of other things. You hire them to handle reporting, query tuning, backup and disaster recovery plans, right? So tuning is only a sort of small part of what they have to do, but it's oftentimes not the most pressing thing because you want to make sure that your backups are working correctly. And a lot of times they spend most of their time on those things and never get around to doing tuning really well. It's also expensive too. You're basically hiring someone to babysit the database system, right? And that's why you don't see a lot of these DBA roles in sort of Silicon Valley style startups or companies, because you rather have a programmer help you build out your application, because that's going to affect the bottom line or affect your revenue, whereas the DBA is sort of just making sure things are working correctly. And oftentimes that gets overlooked. All right, so there are some automated tools to help you. So the first are rule-based tools where you punch in some basic information about your hardware, how many CPU cores you have, how much RAM you have, what maybe your workload looks like. And then they have these formulas that are written by database developers that produce or spit out sort of approximation of how to tune a select number of knobs. So the commercial vendors all have their own tools. So SQL Server, Oracle, and DB2, and essentially they all work the same way. On the open source world, there's a MySQL tuner tool from Percona, and then there's the PG-Tune website that does essentially works the same way. So what I'm working on what I'm pushing is the better way to do this is to do machine learning. We take a black box approach to the database system and rely on statistical methods, machine learning algorithms to produce better configurations. The reason why it's called black box is because we don't need the algorithms to know anything about the internals of the database system. All we need to do is just extract out all the information about what the system is actually doing, and that's enough for us to figure out how to tune it correctly. So for this talk, we're going to focus on this one. So OtterTune is an automated database tuning service that we developed at Carnegie Mellon. And it was my PhD student's core topic for her dissertation, and we've since spun it out as a company. And again, the core idea is what I showed in the last slide, is that we're going to use machine learning algorithms to automatically figure out what the best setting is for some knobs for each individual application. And this is going to allow us to improve the performance of the database system and also reduce the cost of actually running it, whether it's on-prem or the cloud. So before I describe actually how it works, let me go kick off a demonstration for you. And then so while I'm going to give the talk, we'll let OtterTune run in the background and try to tune Postgres or optimize Postgres. And then we'll look at the end and see how well we did. So for this one, we're going to be running Postgres version 11 on Amazon RDS. So this is Amazon's hosted version of Postgres. And we're going to be running the standard TPCC benchmark, running on the EC2 instance. So just to show you this is real and a live demo. So this is just a terminal running the system. So we're using the OLTP bench implementation of TPCC. It's basically a JDBC implementation that runs the transactions over SQL. And then we will have this web interface that we'll come back to later of the system. So I kicked it off before we started. So you can see at the very beginning, the default configuration got us 839 from Amazon. And then within 2 iterations, we're at 1900. So we're going to let this keep running in the background and see whether we can do better than this. So this first number here, the first measurement is the configuration that Amazon gives you when you run it on RDS, right? So Amazon's already actually tuned this. It's better than the default configuration you get for Postgres on, if you install it on Ubuntu. And that's very conservative about what your hardware looks like. So Amazon's already done some tuning, but again, within 3 iterations, we're able to get better performance. So again, it's going to apply a configuration and then observe what happens, and then repeat the process. So again, this will run in the background, and we'll keep going with the talk. Okay, so the way it works is that you have your target database system, and OtterTune supports Postgres and MySQL, and as well as Oracle. And the first thing that has to happen is that there's a controller that connects to the database. It has to have permissions to retrieve the PG statistics, or all the stats that the system's collecting, as well as the current configuration. We also can connect to Amazon's RDS hosted platform and get all the OS measurements that they're recording as well. So the controller is going to collect this information and then ship it over to our tuning service. We're going to store this in our own internal repository of every single tuning session we've ever done for any database ever. And then we're going to use that data to train statistical models that can predict how the database system will perform as we change the values for these knobs. So you have to tell us in the beginning, I want to maximize throughput, minimize latency, minimize costs. That's your objective function. And then we can train a model that can predict how that objective function will change as you change the values to these knobs. And then we run our recommendation algorithm, which is gradient descent over the models, to then produce a new set of values for the knobs that we're tuning. We ship that back over to our installation agent, apply the changes, flush them, and then repeat the process. So this can occur multiple times, because every single time we add a new configuration and try it on the database system, we'll learn whether things are getting better or not. So the 2 important things to point out here. So first one I've already sort of said is that this is a loop system. We're repeating, trying out configurations and seeing whether they get better until we think we converged. And we're storing all this data in this internal repository across all the systems, all the installations we're tuning. So that means that for each new database that comes along, we may be able to tune it much more quickly than having to tune it from scratch every single time. So the idea is that if you come along today with a database we've never seen before, but we can determine through our algorithms that it looks very similar to a database we tuned last week. Since we know how to tune that one, we can now tune yours more effectively and more efficiently. And over time, our models are getting better to produce results more quickly and with better improvements. The other important thing is that the data that we're collecting from the database system is just the statistics, the metrics of the system, and its current configuration. So again, these statistics are just like the internal performance counters of the database, like how much data did I read and write from disk, transactional information, things like that. So that means we don't need to look at the user data, and we don't need to look at any of the queries. So there's no privacy or security concerns of shipping sensitive data over into our service. And for the 2 deployments that we've done, we're both in Europe, and they fall under the EU restrictions for moving data outside the continent. And when their security people looked at what OtterTune is collecting, they thought it was benign and there wasn't any issues. All right, so these are results that we published in SIGMOD, which is a big academic database conference back in 2017. We're comparing OtterTune versus a bunch of different methods for how you could tune your database system for both MySQL and Postgres. And this is running on self-managed database installations on EC2. And so the first bar is the default configuration that you get from Ubuntu or the OS or the package, the package library when you install the database system. And as I said, they're very conservative about how much hardware you have. So that's like MySQL's case, they assume you have 128 megabytes of RAM, which nowadays it's not real. So that's why the performance is really bad. The next one is the open source tuning scripts. Again, the one for Percona and then PGTune. The next is the RDS installation. So this is the configuration that Amazon gives you when you deploy the system. And then for the DBAs, for MySQL, we have the top MySQL DBA from Facebook, who's very expensive. And for Postgres, it was a DBA from the Wisconsin court system, which is a big Postgres shop. And then, of course, the last one is with OtterTune. So the main takeaway from these 2 graphs is that OtterTune can match or exceed what the human DBAs can do without having to be, pay for a human to do this. In the case of MySQL, the reason why the DBA beats us is because there's a configuration knob in MySQL where you can turn off f-syncing or flushing the log to disk anytime a transaction commits. And in Facebook, they're allowed to turn that off. In OtterTune's case, we actually blacklisted that knob or restricted from actually tuning that knob because that's an external cost that the algorithms can't reason about. So the machine learning algorithms don't know whether it's okay if your transaction commits and then there's a crash that you can lose the last 5 milliseconds of data. In Facebook's case, they were okay with that, but in our case, we don't know whether that's okay or not. So we disallowed it from tuning that. But if you do allow to turn off f-sync, of course things are going to go faster, and OtterTune can identify that's the right thing to do. So that's going to be a reoccurring theme as we see throughout this talk, is that there are things, OtterTune says, if you let me tune this, I will make things faster. But we know that turning off disk writes and things like that is probably a bad idea. And so we disallow those things. So this is another study we've done where we actually now see how well we can tune the RDS version of Postgres that Amazon provides. And so this one we want to see, can OtterTune not only improve performance, but also reduce the cost of running on RDS? Because as you may know, Amazon charges a lot. These things are very expensive. So the first line here is going to be the value, or the throughput you get from running TPCC on RDS using the M5 4x large with 4,000 provision IOPS. So the way Amazon works is that you pick your instance size, and then you can also, there's a little slider specify how many provision IOPS that you want. So for this one database, we can get 2090 transactions a second for TPCC, and it's going to cost us $17,000 a year. So in the case of OtterTune's case, we're going to give it a smaller instance size that's cheaper, and we're going to reduce the amount of provision IOPS, and then we're going to let OtterTune tune it and see whether we can match it. So in this case here, the first measurement is what the default configuration you get from Amazon, but then over time, as again going through this looping process of getting feedback as we tune the system and seeing whether that helps or not, and start converging towards the optimal solution. So in the best case scenario for OtterTune, running on this cheaper and slower instance is getting better performance than what you get from the default from a more expensive instance. So in this case here, the cost of the second instance with OtterTune tuning it is half the price, right? So now you'd be saying, oh, well, what about PGTune, right? PGTune can PGTune do the same thing. So this line here represents what PGTune gives you when you run it on the same instance and provision IOPS as OtterTune handled. So even in this case here, because we're tuning it specifically for the application that's running on it, we can beat what PGTune can do. Although PGTune does beat the default that Amazon gives you. So you may say, okay, well, like this is the default from Amazon. Like, yeah, it's better than the Ubuntu default, but I'm not going to run my database with that. There's a large number of people that still don't know that you should be tuning what Amazon gives you for RDS. They think Amazon has already somehow magically made things super optimized. It's not. That's not the case. So there's a large number of people that are still running with the default config, and OtterTune can do better. So the question was, are the synchronous commit and fsync on Postgres also blacklisted? And if so, was it try to turn off these to beat the ML? So for Postgres, again, anything that affects the durability of data and there's an external cost to it, those are all on the disallow list, right? So what I showed before where we beat the DBA, that's without playing any tricks with fsync. All right, so another thing that matters for Postgres is doing kernel tuning. So there's if you read the documentation for Postgres, there's a handful of parameters in the Linux kernel that you should be tuning for to get the best performance. So we extended OtterTune. We had a master student do a capstone project where they extended OtterTune to not only tune the Postgres knobs, but also tune the Linux kernel knobs, and then measure whether we can get better performance that way. So I'm just going to show one graph from that experiment here. So the first bar is what you get from the default configuration from Ubuntu without doing any kernel tuning. The next one is when we only do kernel tuning, then we only tune the database system, but then the last bar here is when we actually tune both of them. So although the commercial version of OtterTune that we're releasing this month isn't going to be able to support tuning the kernel knobs, it's the same kind of problem. It's something we could extend it into as well, potentially in the future. we spent a lot of time trying to determine whether it made sense to tune the OS first, then the database system, or tune the database system, then the OS. It turns out you want to sort of treat them all sort of as one system and tune them together to get the best performance. Okay. So we had, as I sort of mentioned, we had a paper come out in 2017 in SIGMOD. And when that paper came out, the other academics were like, oh, this seems like a good idea. People, were sort of interested in it, but nobody in industry paid attention to it. And then we just happened to meet the guy that runs all of Amazon's, machine learning AI division. And I got 5 minutes of his time just to thank him for giving my PhD student, a couple $1,000 to run her experiments on EC2. And he was like, great, we started the new Amazon AI blog. Can you write an article for us? So this page here is just a summary of what that academic paper was about. But when this thing came out, then everyone in industry now saw it. And we got all sorts of crazy emails that were basically saying like, this is the greatest idea ever. We want to give you money to fly out a student to help set up OtterTune for us. We have this exact problem. A bunch of people were like really shady about wanting to give us money to do a startup, which is, I was still a sort of junior professor, so I wasn't ready for that. So we got a lot of crazy emails. But then we got actually a very useful email or interesting email from somebody at a major French bank who was looking to deploy OtterTune on their large Postgres installation running in their data center in Paris. So this is the first field study that I want to talk about. So again, this French bank reached out to us and they told us that they had 1,000 Postgres installations that were running in their sort of self-provisioned deployment environment in their data center in Paris, and they wanted to use OtterTune to tune it. Right. So the way it worked was like you would go out to their internal IT website and say, I want a Postgres database. Click what how much RAM or CPU you wanted, click go, and then it would spin it up for you. So they had this giant fleet of Postgres databases, and they wanted us to tune it. So we were like, great, OtterTune supports Postgres. Let's do this. So it was a research collaboration. We didn't take any money from them. My PhD student worked with the bank, took on a French master student on site to get OtterTune up and running. And after a couple of months, they got it to work. And so then now they said, let's go actually look at those Postgres databases and see whether get OtterTune working on them. So it turns out, although they originally told us 1,000, the real number was like 1, because what happened was the bank had this big initiative a few years ago where they said, we need to start using more open source software. And that means that for every new project in your budget justification, you had to specify what open source software you were using. So the word got around the bank. If you click the checkbox and say, I'm going to use Postgres, it would spin up a Postgres instance in their self-provisioning infrastructure. And then you never had to put any data or run any queries on it and just use Oracle and pay Oracle like you normally would. So they literally had 1,000 Postgres installations running in their data center with nothing in them. So that was a bit of a bust. So then they came back and said, okay, well, you can't tune Postgres. We don't have anything that you can touch. We're primarily an Oracle shop. Can you make it work on Oracle? So for this one, so it took about a couple months. We had a student at the university extend OtterTune to work on Oracle. And that doesn't mean we have to change any of the machine learning algorithms, because they don't care, one database to the next. It's all the sort of the front infrastructure for connecting to the database, reasoning about its parameters and knobs and so forth, and extracting the information that we need. That's what actually takes the most time, because you need to understand what the machine learning part wants and what the database is trying to give you. So they gave us a 1 terabyte database that had actually already been tuned manually for query tuning, index tuning, and knob tuning by their in-house expert DBAs. And for people that don't know about Oracle, Oracle has this proprietary metric they call it DB time, and this is what people use to measure the performance of the system. So it's just an amalgamation of wait times and latencies of different parts of the system. There's nothing equivalent in Postgres, but this is something that the Oracle DBAs do. So the way this would work is we would run our controller. We would start the database system, immediately check the log to see whether something bad was happened. I'll explain what that looks like in a second. Then we would reload the database from a snapshot, but then we would run these I/O benchmarks, essentially running FIO, to measure the performance of the disk the database was accessing. We had to do this because all the Oracle databases were running on shared disks for regulatory reasons. Like the bank was not allowed to have, any VM couldn't have local storage. You always had to go to a single location because it could then be audited. But the problem is this thing was on a shared network, and depending on who was next to you and whether Bitcoin mining or writing a lot of data, that can affect performance. So in our FIO measurements, we saw a high, standard deviation in the difference of the performance of this disk, like up to like even 3x performance difference. And the challenge from a machine learning perspective is the system's not going to know, the service is not going to know, did I try this config and I got bad performance because it was a bad configuration, or is because something was going on in the disk and at the time and things got really slow. So we tried a bunch of different methods to try to normalize this data to account for these fluctuations in the shared disk architecture. It turns out the answer was just more data running on more machines in order to smooth this out. So this is less of an issue on Amazon. Amazon's bounds are much tighter than the bank had, but if you're running on-prem, this is always an issue. All right, so then we would collect the metrics from the system. Again, this is just retrieving the internal performance counters of the system. We run our workload trace and then compute the delta between what the stats were at the beginning and after, because there's a bunch of counters, like how much data did I read at the beginning and how much did I read at the end. You subtract them, and that tells you how much data you read when you ran the workload. And then we ship this over to OtterTune. It would then compute a new config and ship it back over. So I'm going to show one graph that we published in DLDB this year that shows the performance benefit we're getting. So again, this database had already been tuned by in-house human experts, and after running the trial for several days, OtterTune was able to produce a configuration that reduced the DB time measurement by 50%. So this is great, right? Like we're reducing the resource consumption by 50%. We go back to the bank and say, hey, look, how much money do you think we'll save you from doing this? And they were like, we have no idea because we've never been in a position to pay Oracle less money. We got to get back to you about this. And they still don't know. But I would say in this case here, like speaking like list price numbers, with this installation, we could turn off 1 or 2 CPUs from the database system. And since Oracle charges per CPU core, that could be roughly from $50,000 to $100,000 savings for this one database annually. All right, so what do we learn from this deployment? So I want to talk about 3 things that came out of the study. So the first thing was that, again, it's no surprise, humans make mistakes, especially expert humans. So what happened at the bank was they had been running Oracle 11, and then they upgraded to Oracle 12. Sorry, they were running Oracle 11, then they tuned the database, and then they upgraded to Oracle 12, and nobody spent the time to figure out, okay, for this one particular database, okay, what has changed going from 11 to 12? So in particular, one of the knobs that they missed was bumping up the version of the optimizer. They were also very conservative about this as well, because there may be regressions in performance when you change the optimizer. There's also another, there's no equivalent in Postgres. Sort of the toast table is sort of like this, but it's not the same. Like in the case of Oracle, there's a separate buffer pool for blobs, for large objects. And if you tune, and for this particular database, it had a lot of large objects. So if you tune that correctly, you can get a big win. So again, like after this upgrade, they didn't check to see whether they should be tuning again because they had so many other things to do because they have hundreds of these databases. So we think the solution to this is obviously more automation. And OtterTune can then be used as sort of a nanny or monitoring service to make sure that your database at a particular time, given the environment, given the workload, you can use OtterTune to determine whether you have the best configuration right now, or we think we should try something else. The other challenge we faced was how to actually replay the workload trace. So they took a snapshot of the production database, they ran it on a separate VM with the same hardware configuration as the production database. And that way we can run all our experiments over there, restart the database as much as we wanted, and not interfere with the production database. And then once we found the best configuration on the clone, it would then get promoted up to the production machine. So the challenge with this is that we had a workload trace of queries we're going to replay, but depending on the configuration we were trying at a given time, that workload replay might take hours where it could have taken minutes, right? Because at the very beginning, we don't know anything about the database, and it takes time for the models to learn some configurations are really bad and some are good, right? And this is what I was saying at the beginning. The more data we have, the better our models get. In the case we've never tuned Oracle before, we had to start from scratch. So the challenge would be that we would try, what should be a 20-minute trace. If we had a bad configuration, it could take hours and hours, right? So we obviously don't want to waste our time trying out a configuration we know is not going to be good if we can observe in the beginning that it's not going to be good. So the way we'd avoid this is just have a cutoff and say, if if my workload replay has taken 3 times as much as I think it should, let's just kill it right now and try a new configuration. But now the challenge is, how do I give feedback back to our machine learning algorithms to say, hey, this configuration we tried before from the database, that was actually bad, don't try it again. If I abort it, if I do cut off the replay early, then some of the metrics I'm going to collect are going to be lower than they would have been had I run the full trace. Like if I'm counting how much data I read and write from disk, if I kill it halfway through, then I only end up reading half the data I should have, right? So now the algorithms could potentially think that, oh, this was actually a good config when it wasn't. So the first issue we've already talked about, again, what if things are slow? But then the next issue is going to be, what if I actually set incorrect values for these knobs and the system is unable to start back up, right? So and obviously if you set a bufferable size in -1, not that the system will let you do that, but like when it boots up and sees -1, it's an invalid value and it'll crash and refuse to start. Postgres does this as well. MySQL, every system has these issues. The more tricky one, though, we haven't seen this in Postgres, but this was an issue in Oracle, is that the system boots up, it thinks at first the configuration is valid, but only later on when it actually tries to do something as you're executing queries, then it says, oh, I'm in an invalid configuration state and has to crash and it fails, right? In the case of Oracle, there's some knob to allocate a different buffer pool for some Java stuff or something. And at the very beginning, when the system boots up, it doesn't allocate that memory, but only like 5 minutes later, then it actually tries to allocate it. And then it would freak out because it had invalid value. So now you got to figure out, was the crash caused by the configuration or was it caused by an actual bug in the system? So then again, and now we need to provide feedback to our algorithm so that we don't try configurations that will lead us to have these issues in the future again. All right, so how do we identify there's a failure? So in the case of Oracle and Postgres and MySQL, we scrape the log and see when we come back up, if it fails to start, is there an error message that says something bad has happened? It's not ideal, but it's the best. It's the only thing that sort of exists now. But then the tricky thing is, how do we then incorporate the results from the bad configuration back into our algorithms and say, okay, don't try this again. So the solution to this is just to say the objective value measurement from the bad configuration is the same as the worst configuration we've ever seen. We tried doing twice as worse, 3 times as worse. That makes a difference in the machine learning world for some different application domains. For databases, we haven't seen being an issue. And basically the idea is you don't want to set it to negative affinity because now in your solution curve, you have a hard cliff that goes to infinity. And that messes up the machine learning algorithms. So this solution seems to be good enough for us. Okay, so the study at the bank that was published in DODB, it came out in March, and there's a paper on our website that talks about this if you want more details. But now I want to talk about a sort of commercial deployment of OtterTune since we spun out the startup and sort of seeing something beyond just something from a research perspective. And so for this one, we were reached out to by a major travel website that you all know, have heard of, and probably used, but I can't say who they are. And they had a large cluster of MySQL databases running on-prem in their data centers, and they wanted to use OtterTune to see whether we can improve performance and help with consolidation. So they actually originally reached out to us before the pandemic and said, hey, we want to optimize our MySQL 8 installations. Then the pandemic hit, our main contact disappeared. It came back in June and July and was like, hey, people aren't traveling anymore. We're hemorrhaging money. Can you help us do server consolidation? So these machines are running on the back end. So it's not hosting the website. It's hosting all it's the back end internal services that they use for analysis and bookkeeping for their site. So it's a read heavy workload, and we're retuning the read replicas. So it's all read-only queries, but then when you replay the log, you do updates. So what they already had in place was a bunch of Puppet scripts that had in-house formulas that they generated, similar to PGTune or similar to the rule-based tunes, where they said, if I have this much of RAM, this many CPU cores, here's how to set some number of the knobs. And then in some cases, they went and also did additional manual tuning, but that was done on an ad hoc basis. So, they're primarily a MySQL shop, and the reason why they wanted to use MySQL 8, actually, which is interesting, is they were migrating from 5.7 to version 8, and from OtterTune's perspective, version 8 is better to tune than 5.7 for MySQL because version 8 exposes way more metrics that are useful to us to improve the accuracy of our predictions in our models. So they wanted to tune 20 knobs. 19 of them are going to be dynamic. 4 of them are going to be static. So dynamic means that I can make the change or change the knob, and I don't have to restart the system before that takes effect. And the static ones are ones you change, and then they don't take effect until you restart the system. Postgres has the same issues. The commercial guys all have the same issues. Which knobs require restart or not, it's exposed to you in the documentation, but OtterTune is aware of which knobs, whether or not it's allowed to restart. And if it's not allowed to restart, then it won't tune any of the static ones. And so for them, they wanted to do consolidation of machines. So the target objectives were maintaining the same P99 latency of the queries, but also trying to reduce the number of concurrent threads and the CPU utilization of the system. And because this was running in production, we were only allowed to tune between 9 a.m. to 3 p.m. window European time, and then we were only allowed to do 1 restart per day. Again, the French bank was running on clones that were never touching any production machines. In this case here, they're read replicas. If we restart and the data system's down, there's a load balancer to send the query somewhere else, but they didn't want this thing to be churning all day. Right, so the setup was, as I said, it's a read replica pool. Our controller collects the metrics from both of them, from both the tuning database and the control database. So because we don't have a standard workload that we can replay over and over again and know whether we make a change from one replay to the next, whether things got better, it's a continuous stream of queries showing up. We needed something to say, sort of a control machine to say, yes, things are getting better, right, relative to that. So although they're not executing the exact same queries, it's coming from the same application domain. So the queries are similar enough. And with over enough time, with enough measurements, you can assume that the workloads are exactly the same. So we have our database that we're actually going to tune, and we have a database that we're never going to touch, but this is just determining whether, at a given point in time, are we making things better. So we collect metrics from both, and these are going to be a combination of InnoDB stats and then the Telegraph stats, like CPU utilization and OS level measurements that they would then generate and spit out to Prometheus. So we would connect to the host and get this information and include that all in the data that OtterTune collects. All right, and then we would then wait for a little bit, observe the changes, or observe the measurements again, compute the delta like we did before, and then ship this over to OtterTune with the last configuration that the tuning database was running. Our algorithms run, generate a new configuration, and apply the change, and then repeat the process. And if it's the allowed restart time in the day, then we would essentially also restart it. So again, we never touch the configuration on the control database. We'd only touch the tuning database. So the measurements we got for 2 different applications are actually quite remarkable. So in the first application, this was just our first trial to see whether it actually worked. And we're actually able to reduce the CPU utilization and the number of running threads by over 20%. And at their scale for these read replica pools, this kind of reduction in utilization actually starts meaning like turning off multiple machines. So the pool maybe had like 25 read replicas. With back of the envelope calculation, with OtterTune tuning their database, they can at least turn off 2 machines in this pool. But now they have hundreds of these pools, and this starts to rack up to be a big saving in both licensing costs for Oracle, wherever you're getting your maintenance or your maintenance support contract, as well as turning off machines, turning off, saving energy. And at their scale, this is a big win. For the second database here, we're actually only able to really reduce the P99, and the reason for the smaller improvement is because the amount of queries per second that the second database is running for the first one is much lower. So all the optimization OtterTune is doing is getting less of a benefit, whereas this one is more high load and makes a bigger difference. All right, so what do we learn from this deployment here? So the first issue is that there are, as I sort of said before, there are external factors in the knob configuration that we have to account for, which is not always readily available to the machine learning algorithms. So I already talked about the fsync case where if you turn off fsync, things go faster. And of course, we don't want OtterTune to play around with that unless a human says it's okay to do this. In the case of these MySQL deployments here, it turns out that some of the knobs are sent a certain way because of some higher level edict or protocol set up by the company about how to tune things a certain way. So they would actually set the buffer pool size for MySQL for InnoDB to be half the amount of memory that was available on the system. The reason why they did this is because they were concerned about a flash mob, a bunch of queries showing up, and in the case of MySQL, every new connection allocates a bunch of memory, and they were worried about running out of memory if that ever happens. So they set it artificially low. Well, in the case of OtterTune, we identified that you could go up to 85% of the amount of memory, and still you get slightly better performance. But then we also were able to show to them that, okay, even if you increase the amount of memory, here's a bunch of other knobs that actually affect performance more, and you guys weren't tuning these correctly. So this is an example where, like, there's some external cost or sort of external function that's restricting how things are tuned, and we have no way of knowing this unless a human tells us. So the solution to this is that we now expose the ability through the OtterTune interface to set the ranges of values or to toggle things on and off to let us know whether OtterTune's allowed us set things a certain way. The challenge, of course, is that most people don't know how to set these things, right? In the case of the travel website, they have in-house MySQL experts that knew how to do these things correctly and could reason about them. The average user of Postgres is not going to know these things. So that we try to be somewhat conservative in our settings and what the default configuration, the default ranges are for our knob tuning. All right, the last issue we've already talked about restarting. So, and again, the French bank could restart anytime they wanted because it was on a clone. The travel website could not only restart one time a day because it was running in production, and we weren't allowed to restart the weekend, right? The challenge, though, is, for obvious reasons, you don't want to restart because that means downtime, especially if you're running production. But another challenge is that for some systems, you set the knobs a certain way based on what they were before, then you can have a non-deterministic or a random restart time, right? It's not going to come up instantaneously. So in the case of MySQL, there's a parameter that shows the log file size. If it's currently 5 gigs and you send it to 10 gigs, when the system restarts, it says, oh, I was 5 gigs, but now I'm 10. I have plenty of space. I'm fine. I can come back right away. If you set it from 5 to 1, then the system restarts and says, okay, now I got to have to compact the log to get it bound underneath my limit. And then that's going to take time. And depending on the speed of your disk, it could be hours before the system comes back up. So how do we handle this? So the first one is you tell OtterTune whether you're allowed to restart or not, and then you can say what time of the day you're allowed to restart. How many times or is there a counter how many times you're allowed to restart? Like, these are all things that we expose to you now through our interface. And then for how to actually estimate how long it's going to take to complete the restart, this is an open problem that we don't have an answer to because there's a lot of factors. We think the right way to do it is to start measuring the restart time and accounting for other things that are running in the system or the hardware you're running on, and can potentially build a machine learning model that can predict the restart time for a given configuration. And then we can expose that to the human and say, okay, OtterTune is going to tune this system, and your restart time will be X minutes, and they can decide whether that's the right thing for them or not. So the question is, any case studies with SQL Server? No, the most requested database we've had after Postgres, Oracle, and MySQL is actually Aurora, Postgres, and MySQL. And I'll talk about that in a second, but we plan on supporting that next month. SQL Server, people have requested it. It's just not on our radar right now. It's something, but again, there's nothing that we have to change in our machine learning models to do this. It's just we need an in-house expert who knows something about SQL Server. So as we start tuning it and improving that our technology works on that database system, they can help us decipher what's going on. All right, so what's next? As Lindsay mentioned at the beginning, we've now spun OtterTune off as a startup, and we're going to press. Oh.
Andy, your database is now optimized and ready to use.
I always forget that it's on a timer. All right, so let's come back to this. Let's restart or refresh the page. All right, so again, this is the TPCC experiment running on Postgres RDS. Again, the default configuration at the beginning that Amazon gives you is 839, and it looks like the best configuration is 244. So we're getting over almost a 3x improvement in performance from, well, again, with the default configuration for this workload that Amazon gives you, and what OtterTune was able to learn over time and do. So this is the research version of OtterTune. We'll be announcing the new sort of more polished version, the commercial version, next week at Percona. Okay, so let's finish up, and then we can go to Q&A. All right, so what have I shown you today? So I hope I've convinced you that machine learning is a useful tool to help solve the tuning problem in database systems. At really large scale or really complex systems, or even simple databases, it doesn't matter. We think that OtterTune has shown that it can outperform what humans are able to do, right? This is just one database that I tune, and I'm beating what Amazon can do, or what Amazon gives you. But now, if you have a fleet of 10,000 databases, there's no one human who's going to have time to tune everyone individually. And we've shown that as part of improving performance, we're able to actually reduce the cost of running your database, especially in something like AWS. So essentially, OtterTune is allowing you to do more work, or the same amount of work you're doing now in your system, but pay less for it. So you can do more with less. And we think that's an exciting contribution to the Postgres community. Okay, so with that, I'm done, and I'm happy to answer questions that you may have. Thank you.
That was great. Thank you, Andy. I think we have a few questions, a couple of which you may have already answered. So the first one is curious about RDS versus RDS Aurora in the case of auto-scaling DB clusters.
So yeah, so we have not, I don't want to say anything about Aurora just yet, because we just, as a scientist, I haven't done the experiments yet. That is on our roadmap to do in June. There are some aspects of it that are nice, that the restarts are cheaper. From our perspective, it looks like Postgres, or looks like MySQL, because the front end is. We just haven't tuned it to say, what kind of benefit we can get. So again, it's on our to-do list for June.
This one you may have answered just towards the end there, but is there a significant risk of overfitting? When is the right point in time to stop?
So the question is basically, how do I know when OtterTune should stop tuning? And so you can get it, what the machine learning algorithms will give you is a confidence interval to tell you how much better it could think it can do if you let it tune for longer. So the way we envision people using OtterTune is that you would do an initial tuning at the beginning, and depending on the complexity of the workload and the environment, the models will eventually converge. How long that takes depends on a lot of different factors. In the case of the French bank, it took 3 days. In the case of the travel website, I think we converge in. It takes longer. It took about maybe the same amount of time to converge at the travel website, because we were restricted to only be tuning within a certain time window. So what would happen is the algorithms come back with a confidence interval and say, okay, I think I've converged for your current configuration, or to your current environment. I think I have the best configuration you could possibly have right now. But then the system would continue to monitor the database system and can recognize whether the workload has shifted or changed significantly enough, whether it would merit another tuning session, right? So like if you add a new feature to the application and a bunch of queries show up that look significantly different than the queries you had before, or that the demands on the system have increased significantly, OtterTune could then kick in and say, okay, let's do another tuning process. So for some workloads, they're static and they never change. Sure, like one tuning round would be enough. We think there's a lot of applications where this thing you sort of basically would want this running all the time, similar to like Vivid Cortex or the other monitoring tools that are out there.
Great. Any case studies, OLAP style or TPCH?
Yeah, so in the first paper, we did run TPCH on that. At the time, that was the 2017 paper was with Postgres, I think 9.2 or 9.3. So it's before the parallel worker stuff, before a bunch of the JIT optimizations that they added. So we didn't really see a huge improvement for running OLAP on Postgres. We did look at the I think version 11 was the most recent one we tried this out on. And you do see some improvement. Oftentimes, though, in the case for OLAP stuff, like the disk speed is the biggest issue. So changing the amount of provision IOPS would be a big benefit there. So OtterTune cannot do that just yet, but if you think of provision IOPS, that's just another knob Amazon exposes to you. So that's something where you can say, okay, well, I'm not getting the performance that I want, but if you let OtterTune say, hey, you have this budget, you can spend this amount of money on Amazon, make sure I get the performance that I want, we can then improve the OLAP stuff that way.
And our final question is, have you ever seen any surprising and or counterintuitive knob values after running OtterTune?
Yeah. So I give one example from MySQL. In MySQL, there's a knob that's turned on by default. It's called InnoDB Adaptive Hash Index. And if you read the documentation, this sounds like, oh my gosh, I totally want this, right? Like it basically builds a little in-memory hash index for keys that are accessed quite often. And then you can specify how much memory it has and so forth, right? And it's turned on by default. In the case of the travel website, they had it on for some of the databases, and it actually should have been off, right? Because the workload pattern is a certain way where like this thing was actually hurting you because you have to maintain it and it's taking memory away from the buffer pool. So that's one that we thought was surprising to us. And again, if you go read all the blog articles to say how to tune the database, either they mention it and say, yeah, leave it on, you probably want this, or they don't mention it at all. Where we have found in some cases, it makes a big difference to turn that off. In the case of Postgres, I don't want to say anything just yet about it. The vacuum stuff can be tricky as well to get that right. And there is an external cost to this, so we have to be very careful about tuning the vacuum, which I don't want to talk about it now. Like if you turn off the vacuum, of course, things are gonna be fantastic until it's not, right? Until you run out of space and you have that transaction ID wraparound issue. So the vacuum stuff is another one where we feel like some of the blog articles are misleading. And we hopefully be able to talk about that publicly later this month.
Lovely. Well, those are all of our questions. With that, I want to say thank you once again to Andy. This was great. All of our attendees, thank you for spending a little bit of your day with us. Go check out OtterTune. And I hope to see you on our next webinar on Thursday. So cheers. Thank you so much.
All right, thanks guys. Take care. Be safe.